Hi, so this is my GC model for gas chromatography. I'll do a little sweep through so you can see it all. So we have our needle with the injection port, we have the carrier gas flowing in, we have the column oven with the column going through, the detector that leads us to the computer. So yeah, mine's made out of sparkly stars and puff balls and pipe cleaners because my mom's a pre-K teacher and this is what we had at the house. Okay, so we'll start from the top. So the injection port. We have the needle that contains our sample that injects our analyte into the injection port, and the goal of the sample injection is to get the mixture into the gas phase before it starts going through the column. So we rapidly heat the injection port so that everything gets into the gas phase. The injection port that I decided to use for my model is the splitless injection port. This is shown by my closed valve here, which means that all of the carrier gas that flows in will go through the column. And so the carrier gas that's entering the injection port, it is flowing at a slower flow rate through the system so that more of the sample reaches the column. And unlike the split injection that only about 0.2 to 2% of the sample enters the column, in a split-less method, it allows up to 80% of the sample to make it into the column. And so in order to increase the peak intensity, we can do solvent trapping. Now, solvent trapping is done when you have the temperature at the beginning of the column lower than the boiling point of our analytes. So this causes condensation to occur at the head of the column, and the column is then rapidly heated so that the sample enters the column at a concentrated band. And doing so, the solvent trapping can also help minimize the head start effect. So for my column here, I decided to use a polar column instead of a non-polar because the three samples that we're looking at is ethanol, methanol, and butanol, which are alcohols. And alcohols separate better in a polar setting. And so with polarity, since they're polar molecules and I'm using a polar column, this will keep the polar analytes longer on the column in their stationary phase. And so that's why I chose it, so we can get better separation among the analytes. And so when ordering how they're going to come off and who's going to elute first, it's based off their boiling points. So the higher the boiling point, the longer that the analyte will stay on the column. So the order of coming off the column will go from lowest BP to highest BP. And so our first one will be methanol with a 65 degrees Celsius boiling point. Then ethanol will go off the column at a 78 degrees Celsius boiling point. And then butanol will be the last analyte to come off the column with an 118 degrees Celsius boiling point. And so I decided that I wanted to use the temperature program for my model. And what that does is that it gradually increases the temperature from the beginning to the end. So the initial temperature set will help the early eluting analytes to interact more in their stationary phase as much as they can, and that will allow for better separation within the earlier analytes. And then in the final temperatures is much higher, so it's able to kick off the eluents that are late to eluting off, and that will kick them off because the higher temperature will make them want to be in the gas phase more. An advantage to doing the temperature program is that you have control over the temperature set, and it gives you a good resolution within like a reasonable amount of time. And so the fun part, so once our analyte, all of them elute from the column, boom, we have our detector. And I decided to use the flame ionization detector. And in the flame ionization detector, an advantage of this is that it works really well with organic molecules because it has good sensitivity and it has a great dynamic range. So you can use a little or a lot of your sample to get your quantification of organic molecules. And a disadvantage of the flame ionization detector is that in order to maintain the flame, you need an instrument that uses multiple gases. Excuse me. That's able to utilize multiple gases because you need hydrogen to keep your flame going. But then your carrier gases that are flowing through your column with your sample, such as like helium or just air, just anything, you want to be able to have those working in it also, and you need to be able to purchase them all separately. So you need just an instrument that can use all of, that can like utilize all of it. Okay, yes, continuing, sorry. So for flame ionization, it uses a hydrogen flame to burn the analytes that elute off of my column, and this will then produce ions that will change the resistance of the system. So kind of to go further in what's going on is that it detects that ions form when the combustion of the organic compounds in the flame that is generated by the hydrogen and the air. And in order to detect the ions that are in it, we have 2 electrodes that are used to provide a potential difference. We have a positive electrode that is at the nozzle head where the flame is being produced, and we have a negative electrode that is positioned above the flame. So when the compound is mixed, so when it comes off the column and it mixes with the flame, mostly carbon ions are generated, and a current is then produced between the positive and negative electrode that is proportional to the amount of organic compound present. So the current is then measured, amplified, and integrated, and that's when we see it quantified result into our computer down here with peaks, and we're able to look at it through the intensity at the peaks and the area under the peaks to figure out what our mixed up complex mixture quantifies to based on the area under the peak. So I hope that was good explaining. So yeah, this is my model. Thanks.